All right, our data are prepared. So now we just have to build the model. So for build the model. So if all of our data were normal, and there's just no way they are, but if they were, we would use a normal linear model. Let me scrunch this up a little bit so that we can take a look at that. Just to show you, this is not necessary, but just to show you, if we look at these data, so names, the data, we are going to leave out heat and vegetation and groups, so that is 3 and 8 and 10. So I'm going to say I'll apply the data, but get rid of, what did we say, 3 and 8 and 10. So those are variables that are not numeric, so they're not going to be normal anyway. And we're going to provide a function for x, which we will call the Shapiro test x p-value. So we're not going to go into a whole lot of detail here, but we're looking for very large numbers here, and these are all ridiculously small. I mean, these data are just nowhere near normal. So we have to use a generalized linear model, which is, it attempts to build a linear model, but it does not assume normality. And you can look at in the lab document, I will go into this in a little bit more detail, but I'm going to call this the model, and we're going to create a generalized linear model where we are going to try to predict groups. And rather than specify each individual predictor variable, I'm just going to put the little tilde there and the period and a comma, and then say that my data is equal to the data. So it's going to extract groups, which I have created up here, right? And I have added that to my data frame called the data. So it's going to look into this data frame, the data, and pull out groups, and that's what it's going to try to predict. So it's going to try to predict a 1 every place there is a gorilla, and a 0 every time there is not. And it's going to use all of the other variables in that data set as predictor variables. The only other thing I have to do here is say that the family is equal to binomial. So I'm telling R here that my output, my prediction, has to range from 0 to 1. 0 meaning there is a 0% there are gorillas there, and 1 meaning there is a 100% that there are gorillas there. Okay, so I set the model up like that, and I run it, and that's it. We've just built the model. So I will look at the summary of the model, and so we've got a few things here that are interesting. So aspect turns out to be very important in predicting gorilla location. So does elevation. So does ruggedness, and so does slope. And so does vegetation class 3 and vegetation class 4. Nothing else is important. Vegetation class 5 and 6 are not. Distance to water is not. The topographic index we spent so much time calculating is not. Roughness is not. The heat values are not. So we have dumped in more variables than we need. So we need to clean this model up. So to do that, I'm going to open up the MASS library, and I'm going to create a step model where I'm going to do a stepwise regression based on the Aikike information criterion. So we're not going to go into a lot of detail here, but the Aikike criterion is creating the most parsimonious model. Parsimonious meaning all of the predictor variables that I need, but none of the extra ones that I don't, right? That would be the most parsimonious model. The fewest number of predictor variables that I can use without losing accuracy. So what it's going to do when I run this model is it's going to find the one here with the largest. So the least helpful one is heat level category 2, right? There's a 63% chance gorillas don't care. Oh no, roughness. There's a 90% gorillas don't care about roughness. Okay, so it's going to remove that and then calculate the model all over again, and then remove the next one that doesn't matter, and then remove the next one that doesn't matter, and it's going to keep doing that iteratively until every predictor variable counts. So the step Aikike information criterion function is inside mass, so I need to open it here, and then when I run this model, it will take a while to run. It didn't take very long at all. But we have removed, see how many times it has run this model? We started out with an Aikike criterion of 426, went to 424, 422, 420, 419, and that's our very best model there. So if we take a look at that summary, here are our most useful categories. So aspect is helpful, elevation is helpful, ruggedness is helpful, slope is helpful, and the two vegetation values are helpful. These bottom two, I mean, there's a 36% chance that doesn't help us, and a 19% chance that doesn't help us. Although it doesn't matter. These are all vegetation classes that are inside the original variable itself, so it doesn't simplify the model for us at all to remove that. So we have successfully created a model. The next step then is to reformat our data as input values so that we can predict the likelihood of finding gorillas in all of the pixel values in our data set.